Hi everyone. Now let's continue with chapter 9 today by looking at some different situations. For one, we're going to look at shear stresses in circular beams and also learn about this thing called shear flow. So let's jump right into it. So first off, here is a post. And what you might see is that that post has been nailed together. Now, that's obvious. Nails are used to hold several pieces of wood together. We've seen that before. However, what you might not always realize is sometimes we build up beams that way. You'll have a few beams and you'll have some bolts holding them together to make them stronger. For me, that's actually in my deck. My deck extends out over the side of my house. There's some very large beams underneath it, and those beams are made up of wood with metal in between and then some more wood, all sandwiched together with some bolts. And it works wonderfully. My deck hasn't fallen down yet, and hopefully it won't in the future. But the question here is, how many bolts are needed in my case, or nails in the case of this little post, to actually hold it together? Because I really don't want to walk out there one day, and have my deck collapse because there weren't enough bolts to hold it all together. So how do we figure that out? Well, that's a question we're going to be answering today. Now, first off, though, let's jump right into these beams of circular cross-section. So, like this one right here, it's nice and circular. Well, if we're trying to calculate Q, well, we have to figure out what this area is, which is just the area of a half circle. And the 4r over 3 pi, that is just the centroid of a half circle. Now, the weird thing about circular cross-sections is the shear stress does not actually stay parallel to the y-axis over the entire surface, which is why we only do it through the centroid. That's the only point we're going to care about. So we'll find out that shear force and shear stress that's acting at the neutral axis. So, what is that? Well, for a solid circular cross-section, the value of Q is going to be simply 2/3 times r cubed. And that's just taking the centroid and multiplying it by the area, and some things cancel when we do that. So, if we want to, we can also put that in terms of diameter, which looks pretty nice. And then we can actually calculate our max shear stress. So our shear stress max is going to be equal to our shear force times the moment of inertia times Q over the thickness. And we plug that into our equation, and we have right here our shear stress, our moment of inertia, our shear force. We have right here the value for Q that we got earlier, and then we have our value of the thickness right here, which is going to be the diameter. And it comes out to be 4V over 3A. So 4 times the shear force over 3 times the area. Okay, that's helpful. And also, just in case you didn't know, the moment of inertia equation for a circle is right here. So use this to help you. But now let's jump into what I talked about earlier, about how there are built-up beams, we have nails. How do we determine the number of nails to use? So when we build these beams from separate members, the nails, or fasteners as they're usually called, have to overcome the shear force induced in the members by the internal bending moment. There's that shear force, and that shear force is trying to cut through these points where they're joined, and those nails are having to resist that shear force. But still, how many do we need to keep it together? Well, if we look at this little section right here, and this is one of the side X sections, there's that shear force that's trying to cut it off, we might be able to figure this out. So these fasteners are going to have to resist that particular shear force. And that shear force for this little section is going to be something similar to this, where we are just simply saying that, okay, the change moment is equivalent to my internal shear force, not this horizontal shear force, the internal shear force, I know it gets a little bit confusing sometimes, times the distance it's along. And if we do that, then we can say, okay, this horizontal shear force has to be less than the number of fasteners times the amount of force that they can resist. Okay, this is the shear force that these fasteners can resist. So If we want to make a little bit more sense, though, we can maybe try to change things and put it in terms of the spacing of the fasteners, as well as their allowable shear stress, which is normally what you're going to see. You won't see a force that they can resist, at least not most of the time. Instead, you will see a shear stress they can resist. So we can change things then and say, okay, this horizontal shear force has to be less than or equal to the number of fasteners I have times the shear stress they can resist times this area. And this S right here is the spacing in between each of my fasteners. And this is something called the shear flow. And it's just simply a way the shear force per unit length of the beam changes and moves through your particular member. Okay, now this is going to be really helpful right here, so don't forget that equation. Write that one down. And also, this one right here. Both of those are going to be helpful when you're solving these problems. And as I said right here, it's the shear force per unit length, and here's that shear force per unit length. Or you can calculate it this way if you wish. Okay, now what about in these thin-walled members? Now I'm going to run through this because it's not too much left, and I don't want to make a second video just for this. But using what we've just learned, we can actually start to calculate the shear stress inside of a thin-walled member. And the reason for that, and we can figure out the overall system, is because that shear stress has to be parallel to the face. So if it's right in here, it has to be going down because that's parallel to the face. Over here, it has to be going to the side because that's parallel to the face. It's always parallel to the face. And so all shear stresses that are parallel to the face, which is all of them in these thin-walled members, can be calculated simply using this formula, which is simply the shear flow over the thickness. What is the thickness at this point right here, or right here? If we know the shear flow and we can divide by the thickness, we can actually calculate our shear stress at any particular point we want. So what you do then is you keep on cutting. You cut at a particular point you care about. You calculate the shear stress there. And you cut over here, and you calculate the shear stress there, and you cut here. And you keep on going through until you have a good view of what the system is going to be. Okay? A good view of what the system is going to be. And then eventually, depending on what you're doing, you'll have the shear stress for the entire system. And this works for any particular thing. For some, it's not easy to tell where to start. Like right here, at least you had a corner, you could choose to start there. For these squares, start along an axis of symmetry, because an axis of symmetry, either your shear stresses are going towards it, and they're going to be zero when they get to it, or they're going to be going away from it. Either way, it goes to zero at that axis of symmetry. And that's the same thing for these half circles too. There's a nice axis of symmetry, start there, and go with it. And finally, once you've done this, you will have the overall stress and shear flow diagram for your particular system. Okay, so we'll end it there for today. Thank you for listening, and I'll jump into some examples and some group problems next time. So have an absolutely wonderful day, and I'll see you all later. Bye-bye.